Okay, so video 3, which is the decay equations and some of the mathematics of radioactivity. So we have a couple examples of sort of solving your own decay equations. Here, 222 radon. So radon 222, it's decaying down through alpha decay, but we want to know what it's decaying down to. So the key to these questions is you want everything at the top to add up, so the masses, and you want everything at the bottom to add up. So 222 minus 4 is going to be 218, and 86 minus 2 is going to be 84, and if you look up element number 84 in your periodic table, you'll find it is polonium. So that is the answer to that one. A similar type of question is like this. They give you what the main product is, and they ask sort of what type of decay is this, what particle is being spit out. So 214 bismuth is going to 214 polonium, going from 83 to 84. So it's going to be 0, and you're adding 1 here, so it needs to be minus 1 here for that to, so 84 minus 1 is 83, because you want it to balance. 0, 1, that's one of your electrons, so this is beta decay. So those are really easy. Add the top, add the bottom. You know now electrons are beta, positrons are positron emission, alphas, and too easy. So moving on to something a bit more interesting is the mathematics of decay. So radioactive decay follows an exponential decay pattern. So you start off initially with 100% of your substance, and it decays down. So every interval, which is what's called a half-life, you're losing 50% of your substance. So between 100 and 50%, that's a half-life. Between 50% and 25%, which is half of what you started from here down to here, that's another half-life, and another half-life to get to 12.5%, and so on and so on and so on. So that's the concept of exponential decay and a half-life is something that you have to understand here. And there's some equations associated with that. So the first is pretty simple. The activity of the substance, so that's the decay events per second measured in Becquerels, is equal to a constant times the amount of stuff there. So the more stuff you have there, the more decay events per second in your stuff. That makes sense. And the constant varies on what substance you're using, how radioactive it is. There's another unit you can use for activity, which is the Curie, which is basically just a way of making your numbers a bit smaller. If you have millions of decays per second, the Curie is defined as so many decays per second, so you might have 2 Curies or something. But you can learn that those specific numbers are just scaling factors, and they're usually given to you in any exam, so you don't need to worry too much about them, because they'll have them on data sheets. Another really important equation, and you should be able to rearrange it, is that the half-life is equal to the natural log of 2 over the decay constant. So our decay constant up here can be worked out from the half-life, and the half-life can be worked out from the decay constant. That's probably one of the most important equations in radioactivity, and you need to rearrange it sometimes so that lambda equals log 2 on T half. So you remember either, and you'll be able to get the other. So if you solve the activity equation, so activity is the change of the amount of stuff you have over time, you can solve that using a differential equation to get this equation. The amount of stuff you have at some time t is equal to the amount of stuff you started with times e to the power of negative lambda t, where lambda is again your decay constant and t is the amount of time that's passed. So we're going to do an example with that. So we start with 1 mole of radioactive substance. T half is 30 days. How many is left after 47 days? So that's a pretty reasonable question. the working is here. So you have a t-half of 30 days. So your decay constant is the natural log of 2 on your t-half. So the natural log of 2 on 30 is 0.0231. So n after 30, the amount of stuff after 47 days is equal to n0 times e to the minus 0.0231 times 47. N0 is equal to 1 mole. You can leave it like that. You don't need to do 6.022 times 10 to the 23 particles or whatever. It can be 1 mole. You can do it. You can ignore N0 almost and just work out sort of percent of what you started with. So N0 is pretty flexible in what you plug in there. So N47 is just equal to e to the minus 0.0231 times 47 equals e to the negative 1.0856, which is 0.3377 moles. And that sort of makes sense because going back to our little thing, it was sitting in between one half-life and another. So this is 30 days, this is 60 days, so it makes sense that it's somewhere between 50 and 25% of what you started with. So 0.3377 moles is a number that makes sense as well. So that's very important to sort of double check your answer by seeing whether it makes logical sense. So that's all for that.